Okay, so welcome to this new session of our probability seminar. Our speaker today is Armand Bernou from Université de Lyon 1. Armand is spending some months here at CMM for 1 month or 3 weeks. And well, he works in the propagation of chaos, and he's going to speak about the propagation of chaos and relaxation for interaction of them. Thank you.
Okay. Thanks a lot, Joaquin. Thanks for hosting me for a few months and for the invitation to speak here today. So I will speak about some mean-field models and actually some quite easy mean-field models in some sense. So the idea is first to give you a sort of overview of what's going on in mean-field models, roughly what are the main questions. And then to focus on a very nice setting and to try to extract as much as we can in this very nice setting. So this is from a line of work that we're doing with Michael Durance, and I will also mention some results with Mathieu Ménard, who is in Paris Cité now. So the idea just in general is that I will consider interacting particles that will interact 2 by 2. Okay, so the idea is just at first, let's not put any noise or anything. I just have n particles interacting 2 by 2 through some potential. Here I wrote it as the gradient of some function w. And historically, this kind of models have first been considered for plasma physics. But actually, over the last, let's say, 2 decades, there's been an explosion of applications with things ranging from biology. I mean, you have studies of things like flocks of birds, crowds, also for local neural networks in the brain, and for artificial neural networks, typically where you study, one layer network but with a large width. So this creates kind of different challenges because the scales of those models are quite different. If you think about a flock of birds or local neural networks, you will typically be in the range of 10 to the 2, 10 to the 3 particles. But if you think of plasma physics, then your scale is the Avogadro number, so it's 10 to the 22 or 10 to the 23. So the challenges are quite different depending on the scale you're looking at. If you have a model with 10 to the 23 particles, it's just too much to simulate, right? And so what you're trying to do is to find an average description of the system that will be tractable. And this, was the motivation originally for this kind of mean-field models. But now we kind of say the other thing, which is that if you use this approximation with a too small of a number, let's say with 10 to the 3 particles, then you have some error. And then something that you would like to do is to be able to quantify this error and eventually to refine the kind of approximation that you're doing. Also, of course, it's very natural to introduce a noise in this kind of systems. And this creates a sort of gradient in which you have several regimes that are possible. So just to give you an idea, if you look at plasma in the sun, which as I said was sort of the original motivation for this kind of models, you're typically in what's called a Langevin regime, which is basically you don't see the noise. Okay, just because you have a very dense system of particles, the interaction is very strong, and okay, maybe the noise has some little bit of the particles have some little bit of noise due to thermal effects or anything, but it's really weak compared to the interaction. If you think about flock of birds, so this is actually a picture from the Starflag project, which was a project in which Parisi was involved, that was studying flocks of birds in the sky of Rome. And here it's a little bit mixed because you have, wind effects, this kind of thing. So you have both interaction and noise, and basically they play sort of similar role. So you cannot say that one really dominates the other. Actually, what they found out in this kind of paper is that it's not really everyone is interacting with everyone. So we're already touching that mean-field models are one description, but you can actually refine it. Here it's more typical interaction. So basically what the bird is doing is that it's looking for its 10th nearest neighbor, and it aligns with the mean of this 10 nearest neighbor. So we're already not in a system in which everyone is talking with everyone, but you just have some restriction on the graph of interaction. And then you have, for example, mean-field neuron. So if you look at so this, maybe you can see in the video. So it's from the brain of a zebrafish. And by playing a little bit with the calcium ion, you can really see which neurons are activated. Okay, and so the idea is that this looks more like a jump process because you see things activate, but the underlying potential that is driving those jump process and causing them to pass a threshold or not, and then to lighten up, is actually a diffusion model. And the idea is that neurons are, for those kind of model, neurons are more or less not independent, but they tend to have a very strong personal noise that they use. And then there is some small interaction with the region, but it's not the dominating force. So it's, next. All right, so you have this regime. So you have cases where you have small noise, cases where you have strong noise, cases where the two are kind of in balance. And of course, there is you can always renormalize, right? So strong noise means small interaction, weak noise means strong interaction. It's just a competition between the two. Okay, so overall, those kind of models with particles interacting 2 by 2, they give you a rich playground for mathematical challenges. The idea is that if you consider, I put 2 on the slide, but actually, if you consider a finite number of particles, they will typically become asymptotically independent in the sense that when you look at n goes to infinity, so when the number of particles goes to infinity, you expect that if you're interacting with someone, it really didn't influence your trajectory before, you didn't influence its trajectory before, and so more or less things are independent. So it's an old idea, that dates back to the work of Boltzmann on hard field systems. And then it was sort of refined towards something more applied to Milfield models, first by Kak and then by Makin. And now, for let's say 2 decades, it has become something very active in the mathematical community with several key challenges remaining. So one of them is, of course, that you would like to treat more and more singular interaction. And the sort of goal here would be to be able to treat in full generality the Coulomb kernel, which is, if you want to treat gravity or things like that. You also have like Keller-Segal equations that are singular also because they kind of put this balance between the strength of the interaction and the strength of the noise, in addition to the Coulomb setting. You have the question of geometry. So I mentioned the topological interaction. There is the whole question that if you look at this kind of model for networks, indeed, everyone is not, if you think about a social network, right, everyone is not following everyone. But on the other end, you have nodes that are concentrating a lot of attention and that can really can really influence the network quite heavily, and nodes that are more, that have a lower degree, right? So that they don't speak with a group. Of course, there's also the game layer. There's the whole multi-game theory that I won't talk about. And then there are some other sources of complexity that you can put into the system. So one of them is that you can consider rougher interacting potential. So that kind of ties up with the singularity, but that's another viewpoint. And you can also consider rougher noise, right? Something else than just a Brownian noise. And so, yes, and one last thing, synchronization. So this is the idea that there are some regime in which you can have, for example, you start from, let's say, a cloud of particles very concentrated, and this is what you see, for example, in oscillation model like Kuramoto and things like that. And you see that the particle will arrange in some states, and the state is quasi-stable, as you say. So basically, particle will get stuck into this synchronization framework and stay there for a long time. But this is not the final equilibrium. And there again, this creates some interesting things to say. So here we will take a kind of a different view on that, which is we'll put ourselves in some sense as the nicer setting possible. And then we are going to try to say as much as we can. And the idea is a little bit to pave the way towards what you can expect even for more singular models. Okay, we kind of want to really exhibit the full picture. And then, if you have more singular models, you have a sort of number of properties that you would like to retrieve that will kind of follow the line that I will try to provide here. All right, so let me actually go through the models. So the first model that I want to present is just interaction between particles. So let's say on the torus, but it can also be on the whole space with the confining potential. And the idea is that I have my n particles interacting through some kernel K. And here, instead of writing 1 over n of the sum of k, yi, yj, I put it with the empirical measure here, the 2 here. And then you have a Brownian motion. And the interaction is modulated, this should be a yin here, sorry. And the interaction is modulated by this small parameter kappa. So I'm just saying we have a small interaction, which is equivalent to say we have a big noise. Okay, initially my particles are IID, let's say with the same common distribution mu naught. Let's say this mu naught has some moment. This is some reasonable assumption. Basically, what I will want to consider is the case where K derives from a smooth potential. So K is minus gradient of W with W smooth. Let's say even as well, just to have good properties. And then let's say that kappa will be smooth. So this is sort of the setting for the whole talk. So this is what I call the first order of the non-kinetic model, and you also have the kinetic version. So the kinetic version is now you have each particle has a position and a velocity. The position evolves according to the velocity. This is just the Newton's equation. And then on the velocity, you see the interaction playing a role here. You see the noise, and you see some extra damping here. So this is a friction term, and this is just because I will want to have good long-time properties of my system, and this cannot be guaranteed unless I have those kind of things. So this is why I add this in the dynamics. Okay, and again, I'm starting from initial data that are all the same with some common law mu naught. It's basically okay. So I will. You can forget sort of this model for the whole talk, but the message here is that what I will present for the Brownian system actually applies to this. Up to adaptations, and those adaptations are typically that you have to consider more complicated norms. And this is just because the ergodic properties of a system like that are a little bit more difficult to capture than the ergodic properties of the first order system. Here you don't have a fully parabolic setting in the sense that if you really want to capture the dissipation, then you have to go through like hypercoercivity techniques and things like this. Maybe a view of this Langevin model. So here is a case. I think I have, I don't know, maybe 500 particles here. And the interaction is just exponential minus, the W. So my interaction is minus gradient W. The W is exponential minus x minus y squared, basically. So it's very smooth. The interaction is small. And here, so it's not on the torus, so it's in the whole space with the confining potential. And the confining potential is quadratic. And this will also be a setting in which all of my results will apply.
Just on the terms of particles here are attracting or they are
repulsive? Yeah, they are repulsive one another, but you have the confining potential that is here to be yes, but yeah, but in principle, our results are for small kappa. So actually, it covers both the attractive regime and the repulsive regime, but it's just that it has to be a small interaction. Okay, so you have two parameters in the system. You have the number of particles and the time that enters in the dynamics. And so you have a whole set of questions that is tied to those two parameters. So the standard propagation of chaos question is about describing the system as n goes to infinity, so the number of particles goes to infinity. And having a detailed view of that would mean, first of all, having the propagation of chaos, which is in some sense a law of large numbers. And we'll see that you can formulate it as a law of large numbers for the empirical measure of UNT. Then once you have the law of large number, you want a central limit theorem. So you want to understand the fluctuation around this limit. And maybe, okay, another nice probability you want to have for this kind of thing is concentration estimates. So that's the first part. And then something else that you might want to do, at least for n small, to be able to refine propagation of chaos. So can you find another sort of equation or another limit that will better describe the system so that you are able to actually refine your approximation, at least when the number of particles is small. And of course, there is the time in the picture as well. So one natural question is, if I'm able to write those things as estimates that are quantified, okay, to associate an error to this, can I actually obtain something uniform in time for the corresponding error? And the question is, okay, is it the best you can hope for to have something uniform in time? Is it really reachable? And so Okay, so those are the questions as n goes to infinity, and then you have the question as t goes to infinity. So here, typically, you want to wonder, okay, does the system has the particle system itself at n fixed? Does it have an equilibrium? And if so, how fast is it convergence? And you might also wonder, okay, what is the kind of relation between the two? Okay, is there a way to sort of understand the relaxation problem, so the convergence as t goes to infinity, related to the propagation of chaos problem? And I will also try to say something about that. All right. So let's make things a little bit more concrete. So we have those SDE, and equivalently, I mean, something equivalent to the system is I can consider a probability density of the system. And that would be an equation, a distribution Fn. So I will write everything on the torus, but again, it's valid in the whole space if you have a good enough confinement potential. And this Fn, this probability density, it solves the Kolmogorov equation. And this is basically equivalent to say that it solves this equation or to consider the SDE. These are the same. All right, so I have this. And of course, initially my particles are IID, so everything is symmetric. There's no particle playing a particular role here. And so I can define in a unique manner, I can define those marginal distribution, which are just the typical distribution of K particles inside the system. Okay, and something that will be useful for me as I want to refine those ideas of propagation of chaos, and that I want to introduce now are correlation functions. So what I mean by correlation function is that this G2 here is the information in F2, so the two-particle distribution that is not contained in tensorization of F1 and F1. Okay, so it's the extra information that you gain by looking at F2 compared to the case where you look at F1 times F1. Another way to say that is sort of the default of independence of the two-particle distribution. The three-particle distribution will be the extra information that you gain in F3 that is not contained in any version of F2 and F1 that you combine. This is why you have this symmetrization here, because it doesn't depend on the order that you're considering. So now let's see one way to view propagation of chaos, which is actually sort of the ansatz that Boltzmann itself used for Boltzmann equation. But it's quite similar here. So if I integrate the previous equation with respect to the n-1 particles, you see that here it will commute and give me F1. Here it will commute and give me F1. Here it will commute, but inside this I have xj minus xy. So I have an extra particle. Okay, so it's not so surprising that what I get is an equation for F1 that depends also on F2. And this is the so-called first, actually you can do this at any order, right? So you can have an equation for Fk that depends on Fk plus 1. This is the so-called BVGKY hierarchy. And this is just the first equation of the BVGKY hierarchy. All right, now, what is the idea? We want to replace this Fn2, ideally by Fn1 times Fn1. But what is Fn2 in terms of my correlation function? Fn2 is my two-particle correlation function plus Fn1 tensorized with itself. So if I know, for instance, that Gn2 is converging towards 0, I can just replace this Fn2 by Fn1 times Fn1 plus a term that I throw away because it converges towards 0, and I end up with the mean field equation. So this is the nonlinear Fokker-Pluck equation, which is the mean field equation. I could have written it as an SDE, a nonlinear SDE, which is the Maclin-Vlasov equation, which would be equivalent. And actually, if I do that, I also have an equation for the distribution, which means if I were to look at the SDE, initially with distribution mu, I can call empty mu the distribution of the corresponding process at time t. So this gives me a flow of measure that satisfies this equation. Okay, and now what do we expect? If you have, let's say, expectation of, for any test function phi, let's say smooth. So recall the empirical distribution is nothing but 1 over n of the sum of the delta xi. So just by exchangeability, all the particles are the same. So I end up with this, and this is nothing to do with the delta y. Okay. And now what you expect is that this distribution will look like empty mu naught just because of this and that, because the initial distribution of your yi is mu naught, and empty mu naught is the distribution once you have let the evolution run for a time t. So actually now we have sort of a way to formulate propagation of chaos for mu and t. it will just be to say that these kind of quantities are close to those kind of quantities, and in a quantified way with M. So this is what's called quantitative propagation of chaos in weak form. So propagation of chaos itself has a kind of long history now. But I would say the more modern results begin with probably the lecture notes of Littman, or also the work of Osterger-Gartner at the end of the 80s. And then you have a lot of different techniques. So, for example, here, Madrieux is more like coupling techniques. Gillin is more like functional analysis things. Lacker is more entropic techniques, and so on. For Katz model, which is related to Roberto and Joaquin, also have some work based on coupling. So there's a whole literature where basically there are three kind of results. There are those kind of convergence in the qualitative sense. There are convergence in the strong sense. So in the strong sense, it can mean, for example, for vast assigned distance, you're trying to show that mu nt is close to mt mu naught. Okay, that would be strong propagation of chaos. Here we're looking at weak propagation of chaos in the sense that you can find, for instance, in the work of Michler-Weinberg, which is that I want for all observable in a certain class. So let's say like this. I want to have this kind of control for this kind of things. Okay, and this comes just from what I've shown you before. Okay, and typically what you expect is that this should be of order 1 over n, but then you might wonder how does this depend on t. And actually, a result by Dollar would say is that in the setting that I've presented, if you have good regularity assumption on W, and if you take phi, the test function should be regular enough, you have those things uniform in time. So you have the uniform in time propagation of chaos. And in some sense, this is a complete resolution of the first question that we had as n goes to infinity, which is the law of Larsen. Okay, so now let's try to formulate the other questions with the same kind of observable. So the idea then is that I want to quantify this kind of object, those Gn2, Gn3, and so on, to be able to refine my propagation of chaos. And typically this will be, and it's not so surprising if you think about it, captured by cumulants of the test function. And the idea is the following. So what's a cumulant? The second cumulant is, in some sense, the extra information that you get from looking at the x-square nonlinearity that you don't get from the product of the expectation. The third cumulant of a random variable is the extra information that you get in the expectation of x cubed that is not captured in exponential of x squared times exponential of x and any combination of all. So in a sense, this description is quite similar to what I've told you about correlation functions at the beginning. And so it's not so surprising that you are actually able to show that, let's say, the nth cumulant should look like the nth correlation function tested against something plus an error. And this error is of order n to the 1 minus n. And it's actually important that you have this scaling here because the sort of conjecture on that, which is quite old, actually, that dates from to Bogolyubov in the 1950s, is that those GNN, those correlation function, they should be of order n to the 1 minus n. And if you think about it, it makes a little bit of sense because when I showed you where propagation of chaos came from, I told you, but this is the Gn2 going to 0. And what you've just seen is that propagation of chaos holds at rate 1 over n. So at least this makes sense, right? If m equals 2, you have that Gn2 is of order 1 over n, which is exactly the rate of the lower number that we had before. So the Gn2 describes the propagation of chaos. And if you want to describe refined propagation of chaos, you will go to higher correlations. And those correlations, you expect them from physics to be of this order. Okay, so now I can reformulate my natural questions from before as n goes to infinity in an observable way. So let me take a smooth test function and try to test phi of mu nt against it. So my lower number was that phi of mu nt will be close to phi of nt mu naught with a rate 1 over n uniform in time. The central limit theorem will be to capture the fluctuation around this limit by some process. So we have to identify the right process for that. And then to have a rate in n and to understand how it behaves with time as well. You also have a similar question on concentration. I won't spend too much time on this. And then refined propagation of chaos would be to show that those GMN are controlled by some n to the 1 minus n, possibly uniform in time. And as we've seen in the slide from before, this should be controlled by the cumulants. So the cumulants of the test function should inform on that. Okay, so all of this yes, you would like to get them uniformly in time, and this is sort of the main question that I want to address when M goes to infinity. Okay, maybe to motivate a little bit more this idea of controlling those correlations, let me show you an example. So what happens if you really know that Gn2 is of order 1 over n? You can keep it in the ansatz that I gave at the beginning, where I replace Fn2 by Fn1 plus Gn2. Okay. So now you have an equation. You have the equation for Fn1, which is the usual one, right? This is the initial limit, plus a term, which is of order 1 over n, because Gn2 is of order 1 over n. Okay, so far so good. It's not really useful because this is not a closed equation, right? There is this Gn2 here. You don't know how to compute it. But actually, what you can do is to say, okay, let me go to the equation for Fn2. In the equation for Fn2, I will have Fn3. And Fn3, I can replace it by products between Fn2 and Fn1 and by Gn3. And if I know that Gn3 is small, I can throw away the Gn3 term, and I end up with an equation for Fn2 that will just depend on Fn1 and Fn2. So this is the scary equation on the next slide, which is just obtained by doing the same thing. I have the equation for Fn2, which will have some Fn3. I have replaced here just all the Fn3 by a combination of Fn2 and Fn1. And at the end, I have thrown away the term in Gn3, which is of order 1 over n squared. And so now I have two equations, one for Fn1 and one for Fn2. I know the initial, they are closed, if I'm willing to forget this term. And I know the initial data because initially all my particles are the lower limit. And you can do that. I mean, you can, so those are called Bogoliubov corrections. You can actually do that and then show that indeed the particle system is closed, not to the order 1 over n, to the limit, but to the order 1 over n squared of the system described like this. And you can do that at any order if you have control of the right correlation, right? This is not limited to the second order. And so this is particularly useful if you're looking at small scale systems, because then the mean field limit, the error rate is 1 over n. So if you're looking at something in 10 to the 2, then you are happy to be able to refine it with this kind of. Okay, now let's move to what happens when t goes to infinity. So when t goes to infinity and you fix the n, what you expect is that f and t will converge towards some Gibbs equilibrium, which is typically this functional in the setting that I've given you. And in the same way that I've defined marginals for f and t, I can define Gibbs marginal. And this is just because, again, this is completely exchangeable, so I can define this above. And now a natural question is, okay, let's say the speed of convergence of f1, for instance, towards m1, the first Gibbs marginal. And this is what's called Gibbs relaxation. So there has been some work on that already in 2001 by Malvieux, but more recently, Ederle with coupling techniques achieved some great results. And you have also Guillain, Yugozan by functional analysis and lots of Sobolev techniques that were able to obtain some things as well. And basically, okay, this is, I think, the result of Ederle, but the kind of result that you get is that you have convergence of f and t towards mn at rate exponential, which is where the exponential rate is independent of it. So that's very nice. But you still pay the prefactor n, and you actually can't get rid of it even if you go to f1 against m1, which is a bit surprising. I mean, you could expect that there is this n here for the convergence of f and t towards mn, but it's a bit weird that the convergence of f1 towards m1 should be impacted by an n this way. And just to mention, the situation was more or less the same in kinetic. So for the large mass system that I've shown you, in the sense that you again have those kind of results with an absorption factor. Maybe let me show you what it looks like. So this is the same system as before. And it's a GIF, so unfortunately we will have to wait until it ends up and then fix it again. So it's the same system as before, and on the right you have the distribution of the velocity, which will converge towards an n01 here. So it's the first coordinate of the velocity, and you will just see the convergence now. And you see the convergence is pretty fast. I mean, I think at t equal 8 roughly, things are completely settled for the number of particles that I have. Okay, so this is just to mutilate this.
Sorry?
Yes.
The simulation
you have some scaling so that it converges to the Gaussian with value of 1.
Yes.
What is it, the scaling you need in order to achieve that? Because you don't have a preservation of energy, right?
It's just the velocity one. I don't have, but I have, I mean, this will just be the temperature that you see here that will play a role.
All right.
I think. And this is the one I set at b equal 1.
All right.
Okay, and so we thought about the convergence as n goes to infinity. We thought about the convergence as t goes to infinity for n fixed. And now you might wonder, how does the two things behave with respect to one another? So basically, you have this relaxation at rate exponential minus ct. Okay, let's forget the prefactor for now. You have the convergence at rate 1 over n of f and t towards the midfield limit. You also know some stuff for the limiting object. For example, you know that the midfield limit, if you're in a good regime, like the one I'm considering here, is converging towards its equilibrium at rate exponential minus ct as well. And you might wonder, okay, what happens if I try to look at the midfield limit, the usual one, but then I capture the time limit of those two objects? What happens to the convergence? So the convergence was in 1 over n with uniformly in time. Will it improve it? Will it give me something new if I try to consider this kind of convergence? All right, so enough for the question. Now it's time for the answers. And I will present some results that we have obtained. Okay, so the first one that we did with Mitya was to say, okay, if the initial that is interaction strength is small enough, actually we are able to control those correlation functions uniformly in time. It's just that we have to go to a very weak norm. So this is a negative Sobolev norm with a regularity that depends on the correlation that you're looking at. So it's actually a quite bad norm in some sense, but at least we get the result and it's uniform. And we also get from their concentration estimates. I will not detail that, but it's from the sort of same techniques. And it's actually not completely limited to small interaction. The key idea I will show you in a minute is that you need to have good ergodic properties of the midfield equation. And so there are some cases typically for the non-kinetic system on the torus that I'm working with since the beginning. There are some cases in which you can actually say things even beyond the small interaction case. And I should mention, okay, there are some related papers. I think Mitya did some things non-uniform in time for the system without noise before. And you have this paper by Eshan and Rowan where they obtained the same result, not uniform in time, with an L2 norms instead of this weird W minus LM norms. And the methods were completely different. It was a hierarchical method, and I will come back to that with more recent works afterward. So let me be technical for 5 minutes and show you the main arguments for this. So let me work for GN2. Okay, so GN2 is just, in fact, propagation of chaos, which was already known, but I will just show it as an example because it's the easier case in terms of combinatorics. So if I want to control GN2, as I said, I want to control the second cumulant of some phi of mu t. Or let's say this being a smooth function in the space of measures. And actually, in the system, I have two sources of randomness. I have the Brownian randomness, and I have the randomness with respect to the initial data. Let me forget about the randomness with respect to the initial data, and let me put this B to say that this is the cumulant with respect to the Brownian realization. Okay, and now the key point is the following. So for any functional like this, which is regular enough in the sense of a function acting on measure, you have those kind of expansions that are written here. So this is a functional of the empirical measure at time t. So in this, you have encompassed, the initial activity and what happened with the realization of the Brownian motions to let these animals. And actually, the key expansion, which was already noticed by Chassagnier, Struch, and C, is that you can write objects like this as a leading order term that does not depend on the realization of the Brownian motion. So this is the initial data that you transport along the midfield flow. So it does not depend, this first term, on what happened from the Brownian motion. Plus an error term which is of order 1 over n, and which is some complicated functional. And here, let me write something. This functional is a bit complicated. It depends on the derivative with respect to the measure of this object. But actually, let me just say, okay, but what is this? This is just a function of mu n x. Okay, and now you see that if I'm able to completely truncate this integral of this new function of mu n s, I will basically just say that my phi of mu n t in expectation is looking like phi of mt mu n 0 plus some terms of order 1 over n. Okay, this is the plot. And if I have this, the second cumulant is just the variance. So now I have okay, I'm going to write something completely trivial here. Okay, and now you can apply the expansion for both this phi square if you know that you can put 1 over n. You can apply the expansion for this phi square and for this phi to the square, and so you end up with phi square plus something of order 1 over n minus. And so you see that the two simplify and you end up with something of order 1 over n. So the idea is that you have this expansion. Any cumulant, you can write it with an expansion with moments like this. You can do the expansion for all of the moments, and then you have to collect those constellations to see that you have the right order that emerges. And of course, this is kind of easy to do at order 2, but it becomes much worse when you get to higher order because you have to really see these constellations. So let me again emphasize a bit this expansion. So here you have a first term that does not depend on the Brownian motion, as I said. The second term, which is some phi 2 of mu n s, and importantly, so since it's a phi 2 of mu n s, I could expand it again. Okay, and so I will end up with, if I expand it again, I will end up with a third term of order 1, not depending on the Brownian motion, some term of order 1 over n, not depending on the Brownian motion, and some term of the order 1 over n squared, encompassing all the Brownian motion dependency. And actually, okay, and this is the key point why we are limited to small interaction or to setting where we have good ergodic properties, is that in those developments, you have those kind of derivative with respect to the measure of this object, which is nothing. It's just this phi, where the measure mu n s is transported along the flow for a time t minus s, along the limit flow. And so those objects are described by a linearized mean field evolution. So the mean field evolution will be having h reacting against h greater than w star h. And now, because it's the linearized mean field equation, it's h reacting against the mean field limit mu t itself. Okay, so you have this. And actually, what you need to have to be able to truncate things is that you need some exponential decay. Because if you end up with, just an integral 0t of exponential minus lambda t minus s ds, then you're happy this is of order 1, and this allows you to truncate the equation. So the whole game is that for this kind of linearized evolution, which is not very standard because you're linearizing at the solution, not at an equilibrium or anything. If you have the exponential decay, then you're able to truncate all those expansions and then to recover that the cumulants are at the right order. And so typically you do this perturbatively, and this is why you need this kappa to see. There are a few cases where you can actually do it even when kappa is not so. All right, so this was actually, okay, I think the message of the story is that, okay, the stimulus version is a very robust method, but it was quite complicated. So this is a mind map I drew after we did the paper, but here I presented to you most of the ingredients, which are, you have the science expansions. In the science expansion, you have representations through linearized mean field equation. And because you have the ergodic estimates for the linearized mean field equation, you are able to get uniform time representations. And then, as I said, you just have to collect the constellations. And for this, we had to introduce some graphs. It was a bit technical. And then you end up with an exact description of all those Brownian cumulants at any order. And then you still have to treat the initial data, and this is done through Glauber calculus, which is a sensitivity calculus for initial data that allows you to do the same kind of things to different cumulants with respect to the initial data. Yes, let's go straight to this. These are some numerics. Just for example, if I take this test function, which is just exponential minus x squared over 2, and I try to estimate statistically what happens for those kind of quantities with this test function, okay? Actually, the full cumulus, so just the Brownian one. And I'm rescaling it. So here you have n times kappa 2, okay? And here you have n squared times kappa 3. And you see that this stays very small, right? This is really, really close to 0 all along. This is really close to 0 all along. So you know, for this kind of model, so it's in the Langevin model that I presented from the beginning. And so you see that this is quite satisfactory. And there's also something else that you can draw from there. So if you think about it, the model is starting from something IID, but if you let it run a little bit, then obviously you have correlation in the system because particles have interacted. So this just means that, okay, here maybe there is a little bit of statistical error, so I don't start exactly at 0, but for example, here I start almost exactly at 0. After a little bit of time, there are some correlation. Yet, things do not explode from there. So what you can draw from there is that, okay, but actually it shouldn't require too much that the initial data is really IID, because after a little bit of time, your data are not IID, and clearly the propagation of chaos still holds uniformly in time and the control of correlation as well. So you should expect the same kind of result to hold even when things are not IID from the beginning, but if they are just exchanging. And this is the so-called creation of chaos literature. So there's already a paper by Delmoral and Hugo in 2019 mentioning this kind of phenomena. And very recently, Lukarinen and Voxenma did some related work for CAX model. And the idea is that let's consider just an exchangeable particle distribution Fn0, which will solve my same Kolmogorov equation as in the beginning with this initial data. But now the initial data is not this mu0 tensorizing time. Okay, I'm not considering initial things. And so the question is, okay, I have this tensorization error from the beginning. How does it propagate? Is it preventing the convergence from happening, or is it some sort of daunt? Do I see it at the limit and so on? The result we have with Mathieu is the following: is that actually you keep track of this thing, but it's exponentially done, which is sort of what you expected from the numerics. Okay, so you have this Fm, and it converges towards its infinite limits, and the rate is 1 over n. Okay, so this is the previous law of large number that I mentioned. And now you have this extra error that comes from the fact that initially you're not tensorized, but this error is exponentially done. So basically you lose track of this error over time. And for correlations, we formulated it a bit differently, but it's just, okay, if initially you are not at exactly 0 for this thing, but you have the suboptimal scaling. So you don't have the 1 to the 1 minus n that you expect, but you have n to the alpha 1 minus n, which means at the beginning you have a little bit of extra correlations. Then again, this is exponentially done. Okay, let me move to the next question, which is the central limit theorem. So the central limit theorem picture for those kind of models is very kind of tightened with the so-called Jin-Kawasaki equation. So what is the Jin-Kawasaki equation? It's an SPDE that is describing the evolution of mu and t itself. Okay, so you might say, okay, but it's a bit stupid because if you have an equation for mu and t, right, why do we bother about making approximation and so on? But the thing is, this equation is very imposed. It's a very singular SPDE that doesn't fall into the theory of renormalization of error or in the theory of Perkowski and para-control distribution or this kind of things. So you actually cannot make rigorous sense of this kind of equation mathematically. What you can do though is you can use the equation in the sense that you can say, okay, I know my mu and t is going to look like the mean field limit plus some correction, which should be for the 1 over square root of n, because I have volume motions and so on. So that's what I expect. And then this would give me an equation for this mu t, and I can try to use this mu t to get the central limit theorem. So there's been really a lot of work on this Jin-Kawasaki equation recently. Yeah, I think Perkowski in particular has several interesting works on that, with George Delac and Krem, for instance. And one of the key takeaway is that this is a very bad NZAT studio. Okay, and what I claim is that in our case, it's not so bad of an NZAT, but let me explain a little bit. So for example, at the beginning, I mentioned to you the systems which synchronize. So systems for which you have particle distribution that will go to some quasi-steady state and stay there for a long time. And then they will sort of mix up again, go back to this thing and so on. And this is typically what you lose when you're trying to approximate. So the Dinkovsky equation formally sees this kind of phenomena. If you try to do numerics with approximation of this equation, you will see it. If you use this kind of ansatz, you completely lose it. So this is why the ansatz is bad in some sense, because in those settings where you have, for example, synchronization, using the ansatz will actually kind of ruin, kind of destroy what the Dinkovsky is telling you. But for our case, it's a bit different because we're just trying to capture some fluctuations. And so what could happen is that we will lose a little bit what the full equation should capture, but we could still restore a little bit and then have the central limit theorem. Okay. And so actually, there's a very nice sort of qualitative picture given by this paper of Gerber, Vallely, Iver, Pabiotis, and Schlichting recently, in which they really study this kind of models that synchronize, and they compare what happens because when you read things at the mean field level, at the level of the Kawasaki SPD, and so on, and you really see the key difference. Okay, so for us, as I told you, we will use this and that, and still it will allow us to derive a central limit theorem. So what's the theorem? It's again that if you have a small enough interaction, let's say, then my fluctuation around the mean field limit, so mu t is mt mu naught, so it's really my mean field limit, is captured by some process. And this is uniform in time, and you see it captures not everything, but fluctuations up to the order n to the 1 minus 5. Okay, so it's a Gaussian situation, basically. And here, this mu t is exactly what you obtain if you put the ansatz inside the Dinkovsky SPD. So it's, again, some linearized evolution, plus a little bit of white noise that is coming from the Dinkovsky SPD. And initially, it should start from the fluctuation that you have at 0. Okay, so I think it's a quite satisfactory answer to the central limit theorem in the sense that you're capturing quite well what is happening, and this is uniform. And okay, you could ask what happens if you try to put a little bit more. So in this equation, you use the ansatz, and then you sort of stopped at some order of 1 over square root of n, but you could sort of push the Taylor expansion more to see what happens. And this is something Mathieu is currently working on to see if we can sort of refine this central limit theorem. Okay, so all those results, as I said at the beginning, they are valid for the first order model, so without kinetics, and for the kinetic model, in the torus or in the whole space with a confinement strong enough so that we have good ergodic property. And in fact, all of the results, they rely, on those kind of convergence. So you need the convergence of the mean field limit towards its equilibrium at exponential speed. And actually, it's a little bit more than that. You need the sort of linearized equation that I talk about to converge exponentially fast, because otherwise you are not able to truncate this expansion and change this expansion. Okay, and the small modification, I advertised it a little bit at the beginning, is that if you are in the kinetic setting, you have to use a weaker norm. So it's typically like weighted norm, and things get a little bit ugly. All right, so in particular for correlation, this was somewhat satisfactory, yet the proof was very difficult. I mean, quite technical, and we thought, okay, maybe there is a better way to do it. And actually, the answer was provided to by Xie, who released the paper a little bit after our preprint, in which he was able to obtain, in the setting where the initial data is small, and now the initial data really needs to be small, which is very important for his technique. He has a much nicer result in the sense that now the interaction is just bonded. So before it has to be smooth, now it's just bonded. And it controls correlation uniformly in time in L3. So it's a better norm. It's weaker assumption on the interaction kernel, and he obtains a result. But it depends heavily on the fact that K is small enough, and you cannot treat non-small interaction with this kind of method. So actually, we're quite interested in this result, and so we sort of redid a little bit. I mean, we adapted the thing to work in the kinetic setting as well, and so we were able to obtain the same kind of results in the kinetic setting with some weighted L2 norms instead of this L2 norm. Okay, I don't know. Maybe I won't spend much time on the idea. The idea is just that, before I had the BBJKY hierarchy for my density, you can actually write a BBJKY hierarchy for correlation. So it's this awful object. But actually, from this awful object, it's not so bad because you have a diffusion here. So we typically have exponential decay. And then all the operators that happen here, they are bonded. And so you can kind of run a bootstrap argument, which is just to say initially correlations are very small, and I have some continuity, so they stay small for a little bit of time. And then if I look at what the equation gives me just by a Gromval estimate, I have an extra contribution, but this extra contribution is modulated by kappa. And so if kappa is very small, I'm just able to bootstrap the argument, and I just keep the correlation small with the scaling length. So it's a very simple proof that works if you're willing to accept that kappa has to be very small. And actually, we kind of exploited some more this proof, because we thought, okay, but what about for Gibbs relaxation, for instance? So for Gibbs relaxation, you can do the same kind of things. You can compare the hierarchy that is satisfied by FNT with the static hierarchy that is satisfied by the Gibbs equilibrium, and do the same kind of bootstrap argument. And actually, it gives you almost for free that in the small case, the case of small interaction, you have the Gibbs relaxation from before. And remember, the question was whether we could remove the prefactor n that was in front. And actually, you can do it in this setting. So it's a kind of very powerful tool to really see simply the kind of result that you should obtain if the interaction is small enough. Okay. Okay, and now this allows us to the question that I wanted to address at the beginning, which is what happens to the error related to one another. And again, now what you can do is you have those hierarchy of correlations. You can do a hierarchy of correlations for equilibrium correlations. Okay, you have Gibbs marginal, so you have Gibbs correlation if you want, and then you can compare the hierarchy for the Gibbs for the correlation that you had at the beginning to the correlation at equilibrium, and see what comes out. But what happened is that, so remember the JMN is for the 1 to n to the 1 minus n uniform mean time. But now what you obtain when you compare the two hierarchy is that you see that if actually you have you subtract the equilibrium correlation, so these are those BMN, what you end up with is that you have the scaling n to the 1 minus n, but it's dumped over time. Okay, so basically by capturing the time limits of those correlations, you improve your estimate to have some additional exponential decay. And from there, it's not very, I mean, it's a little bit of work, but it's not really hard to get to this kind of cross error, and to see that the cross error for this object will also be this 1/n that you have for the mean field convergence, time and an additional exponential decay that comes from the fact that you've captured the limits, the time limit of those two objects. So this is the result they have on those cross things. And now there is a funny case, which is when you're on the torus with this kappa equal minus gradient W. So remember, I don't know where it is. Yes. So if you have this one and you integrate things on the torus, then you see that the M1K should just be a constant, I think. Yes. And this is also the case of the equilibrium, so of the limit of mu t, so of the mean field limit of the limit in time of the mean field limit. It should also be the uniform distribution. So basically what you have is that M1 is equal to M, which was my mean field equilibrium. And so if M1 is equal to N here, when I take M equal 1, I just recover that the mean field convergence, so the convergence of F1 towards its mean field limit, will be not of order 1/n, but of order 1/n to the exponential minus ct. So this is, I don't expect at all those kind of results to hold in full generality for any mean field model, but just when you have this particular symmetry that causes you to have this, then you have this surprising improvement. And you know, it's a bit funny because people have been working for 20 years trying to prove uniform in time convergence, so that people were trying to show that time is not preventing you from converging. And what this result is showing you is that at least in this setting, time is actually helping you. So this was a bit of a surprise to us. And okay, so those hierarchical technique, they really rely on the fact that you have small interaction, but somehow if you already know that you have the control of GMN uniformly in time, you are still able to work with the hierarchy to still get the results that I presented here. So you still get the relaxation and you still get the cross error control. It's just that you get it up to some error which is n minus infinity. So basically, for any L, you have a constant CL that goes with L, and you have the same estimate plus n minus L. Okay. And this is a little bit different. It's you use the correlation and the fact that you already know the uniformity control for this guy. You put that into the correlation, into the hierarchy of correlation, and then you see how it evolves with that. All right, and so the results are not limited to small interaction. If you are in regime for which you know that you can control this uniformly in time, then you recover all those results that are presented up to smaller. All right, so just to sum up, so the goal of this was, in some sense, to show the whole picture that you can expect for a mean-field model in general by looking at the nice case, right? And sort of giving a target to what you can hope for more singular models and stuff like this. So basically what we've shown is that, so you have propagation of chaos, but you can actually refine it. You can get things that are uniform in time, at least if you have some good ergodic properties, and you can get central limit theorem in this way. That thing should not, at least for good models, should not depend too much on the fact that the initial data are tensorized, because if you have some good ergodic properties that are dumping things, you should just see the fact that things are not tensorized at the beginning as an error that will be dumped over dynamics. And we also have those kind of new results on the cross error, in particular, that are showing how the two limits behave with respect to one another. And so the next question is, for this part, is sort of basically the sort of conjecture is that every time you have good properties of the linearized equation that arrives in this kind of expansion, you should have all of those results, basically. And so, I mean, we're thinking about exploring overfitting. For example, when you have good convexity of the interaction and stuff like that, you could still recover some ergodicity and the same kind of option. Okay, I think I will stop there. And thank you for your attention.
You are the boss. Oh yeah, the typical story. Okay, I have maybe two short questions. At the end, so what is that allows you to deal with the hierarchy? I mean, do you, for instance, in the first setting of assumption, when you need to deal with it, I mean, completely, or just is this type of assumption or this type of expansion that allows you to?
No. So the expansion and the hierarchy are more orthogonal. It's really two different methods to prove things.
Okay.
So this is the idea is you try to capture correlation through cumulants, and then you have this expansion that allow you to treat the cumulants. So this is the first method. And the second method is just to say, okay, I have a hierarchy for correlation. Let me put some ansatz that it should satisfy something, and let me show that by bootstrap this propagates and things like
that. Funny, because it tells you that in a way you can well, you don't need the right hierarchy.
Yeah. So I mean, we haven't used those kind of techniques a lot, but I expect it to be. I mean, it's very robust, this kind of expansion. Maybe you cannot truncate things the way you want or so on, but I expect this kind of expansion to be actually useful for other things. Maybe even numerically. I mean, the first work of Fastanius Kutse was actually numeric, so they had those expansion and they were showing that that you should expect. I mean, this was sort of yes. So what happens with something like that is that it allows you to describe exactly the error that you should get. And so numerically, you can try stuff where you like remove exactly the error, or you do this kind of Romberg interpolation in which you will play a bit cleverly with your n and the scaling and so on, so that you can solve the error that you see.
Okay, and the second question is that the behavior of the cumulants, is it strictly dependent on the fact that the interaction is binary? I mean, you have because for instance, the kinetic wave equation that we are looking at, it's a third. Would you expect something to change, or?
That's a good question. I don't know. I don't even know what you should expect for the for the scaling of correlation. That's what you're asking, right?
Yeah. At least the hierarchy
Yeah.
is more horrible, of course, because
Yeah.
but maybe from other techniques.
Yeah, but you have I mean, the scaling of the GM, you see them from the BBGKY hierarchy, just the BBGKY hierarchy, because
Yes.
yeah, you see them from there. So I guess if you want an ansatz on what should be the thing, the thing to do is to write the BBGKY hierarchy,
Yeah.
and then to try some scaling and to see if it works or not.
Okay.
Yeah, about the creation of chaos.
Yes.
Do you know of other systems that satisfy this property? Very curious about it.
So you have a property like this for Cox model. So this is the recent work of Lutarinen.
Right.
For Cox model, it's not this one. They take like very special correlation function. Basically, they are looking at energy cumulants. So it's like it's really this, but you should phi to be integral of b square of mu. And they have a similar result like that. So this is the one I have in mind. Other ones I don't know. I'm not sure. I mean, in principle, yeah. Anything interacting and for which you can derive something uniform in time in terms of propagation of chaos should have a form equation of chaos. For the reason I'm saying. Then the question is, can you quantify it in a nice way like this? And this is not obvious. And you see already, I mean, this is not completely clean in the sense that you see to control the nth correlation, you need to have control of the initial 2n-1 correlation. So you need a little bit of extra information to be able to recover a result like this. Okay. And this is just because, again, this kind of uses the hierarchy of correlation, those kind of results. And in the hierarchy of correlations, the nth correlation uses n plus 1. I mean, in the hierarchy, in the equation for the nth correlation, you see the correlation for the n plus 1. And so it's kind of how much do you need to iterate this hierarchy that tells you how much you need to go for this kind of hypothesis.
Okay. Are there questions? Otherwise, let's continue. Sorry. And in the sorry. Sorry. Okay. Ouais, j'avais pas ce mot. Là, j'ai plus compris.
Ouais, vous avez
Ouais.